Okay, let's start. Good afternoon. Last week my son was sick. This week I am sick. I hope next week it's not you who are being sick. You will learn, I think today is the probably most important lecture because we will go very deep into one specific algorithm for machine learning that illustrates really well how machine learning works. And I hope it really makes you understand even the basic idea because behind models like ChatGPT, like large language models. But before we do that, do you remember the times in school where the teacher let you watch some movie? I'm not sure if you enjoyed that. Sometimes teachers were lazy and they think, oh, let's watch a movie. I will do that with you as well, but just for 15 minutes because I just saw that in my lunch break. And I'm not sure to what extent you are following the news. I think I mentioned it last time already. I really think it's a very exciting time right now with artificial intelligence and machine learning. There's so much going on. And I'm not talking just about the applications themselves, but everything behind that, like the infrastructure, the incredible demand for computational resources, so data centers, for the incredible demand for electricity that's required to power these data centers, the costs for this, the societal impact on water, on electricity. You probably have, I hope you do. If not, you really should follow certain channels on YouTube or, I don't know, Instagram or whatever you are using to keep up to date. Because again, I'm repeating myself, but in a few years, when 10 or 20 years, you probably will tell your children or your students that you witnessed this, whatever it's going to be. I'm not sure what it's going to be that you are witnessing right now, but it's crazy. So let's watch the video. It's about a data center that Amazon is building right now, a little bit about the history behind Amazon's data centers and other companies that build data centers. It's 15 minutes long and it covers many, many important aspects. I hope it maybe stimulates a little bit your interest in not following just this lecture, but following the news on this. There's really every day there is a news where you think, wow, how can that be? Just, I think today or yesterday, Nvidia, so the chip maker that is powering almost any AI application, their market value is now $5 trillion. So English trillion, German, that's Billionen, I believe. Yeah. So this one company is worth, I think, more than what Germany is generating or creating in value every year, like the GDP. $5 trillion. And I remember, I think maybe it's just a year ago or so that the value was 3 trillion. And I think then half a year ago, maybe it was 4 trillion. If you look at the stock price, it's going up and up and up. And since, yeah. Oh, there's no microphone for you. This microphone is only for the people online. So, yeah, so you have to be very quiet, especially because I have a slight cold. Yeah.
It's equal, 5 billion. Germany also.
Sorry?
German GDP is also 5 billion.
Ah, okay, perfect. So the value of Nvidia now is pretty much exactly the value that Germany is generating per year, 5 billion. And I forgot to start the recording, I believe. No, I did. Okay. So it's all good. Just lean back. If you have drinks and food, if you haven't had lunch, feel free to do that now.
It's kind of surreal how fast this happened.
It was all just dirt fields and nothing really there.
From the time we put the shovels into the ground to when we actually have...
Let me see if I can make the volume up. No. Well, you have to be especially quiet then.
It's kind of surreal how fast this happened.
It was all just dirt fields and nothing really there.
From the time we put the shovels into the ground to when we actually have large customers building that has been record-breaking in speed and scale.
Behind me is the start of what will be the largest cluster of non-Nvidia chips in the world. And Amazon's newest data center mega project, now fully operational here in New Carlisle, Indiana. These 7 completed buildings replaced empty cornfields fast, in about a year, and are filled with hundreds of thousands of Amazon's own custom Trainium 2 chips and soon Trainium 3 across the US, entirely devoted to running AI workloads for a single customer, OpenAI rival Anthropic.
So they're already running about 500,000 chips in Indiana today. And in fact, it's going so well that they've actually doubled down on that order. And we expect jointly we'll be running more than 1 million Trainium 2 chips by the end of this year.
We got the first on-camera tour inside what Amazon's dubbing Project Rainier, and it's coming online amid hundreds of billions in AI infrastructure build-out announcements. Compute demand is at an all-time high, but some are concerned about a possible overbuild.
Lab after lab, all around the world, our customers are asking the same question.
Can your chromatography software actually do this?
With Agilent OpenLab CDS, it definitely can.
I think they're still building on a proposition that we may not end up seeing be realized. It's just crazy how much building is going on.
These deals all sound great on paper, but they only materialize when they're actually racked and loaded and usable by the customer, and Amazon is incredible at that.
Here in Indiana, this is just the first phase, with 2 more campuses under construction now, for a total of 30 buildings on this 1,200 acres. It'll consume 2.2 gigawatts of electricity, enough to power more than 1 million homes, and millions of gallons of water, which has some local leaders and residents worried.
It's just difficult to keep losing farmland, and this took a lot of farmland.
I was for some of the growth, and my friends tried to tell me, you can't let them come in because once they get their toe in there, they'll want more, and that's exactly what happened.
As Amazon plans out more facilities for Project Rainier in Mississippi and beyond, we sit down with top leaders to ask how this Indiana site came together so quickly, where all that power will come from, and how Anthropic will train its AI here entirely without Nvidia. Just over a year ago, all of this was farmland. Now it's an operating AI data center, one of the world's largest. AWS CEO Matt Garman spoke with CNBC's Mackenzie Sigalos about the project.
This is not some future project that we've talked about that maybe comes alive. This is running and training their models today. Cornfields to data centers almost overnight.
In late 2022, around the time OpenAI launched ChatGPT, Amazon was shopping for a site for some big AI plans, talking to utility companies like American Electric Power. Ashley Savio helped steer the deal through local subsidiary Indiana Michigan Power.
We introduced the concept of an Indiana data center to Amazon, and they basically said, what do you have? So we pointed Amazon to that location and the volume of extra high voltage transmission lines that exist, as well as a very substantial substation.
By the spring of 2023, Amazon was making site visits. A year later, the $11 billion deal was official, the largest capital investment in Indiana history. Amazon broke ground in September 2024, and 7 buildings began full operation in October 2025.
It's kind of surreal how fast this happened.
Big local kickbacks eased the path. The county granted Amazon more than $4 billion in property and technology tax exemptions over 35 years. State legislation, passed in 2019, will save Amazon some $4 billion more over 50 years. In exchange,
the state is going to have a GDP improvement of over $1 billion. And we brought in close to 9,000 jobs already.
While those are temporary construction-related jobs, Amazon said it will create 1,000 long-term jobs, with at least 600 of them paid above the county's average wage.
It was all just dirt fields and nothing really there.
Site leader Josh Salabedra has been building data centers with Amazon for 14 years. He moved to Indiana from the West Coast in 2024 to oversee the build, hiring 4 general contractors to make it happen.
Never seen us do a project this quickly. And that's been the most exciting part of it. We also have a second campus that we were working on as well.
Why so fast?
Why so fast? I think that's the customer demand right now, right? And as we saw AI coming and machine learning coming, we changed it to a different building type.
Big tech companies have been trying all sorts of structures to help them build as fast as possible, like tents Meta's put up as it builds a data center in Ohio. In Indiana, AWS has changed to another building type, adding efficiency and newer tech like liquid cooling for the next buildings under construction now.
It's not just fast, but it is secure and reliable AWS infrastructure. And so it's not a tent out there in a field. It is a industrial enterprise scale data center.
Building out the total 30 buildings here, Amazon says, will take at least 2 more years. When complete, it's expected to consume about 2.2 gigawatts of electricity and millions of gallons of water, which is why local resident Dan Caruso had 100 of these signs made.
We've got water issues. They're uncertain whether the power grid is going to be able to supply Amazon, GM, and the town, and there may be brownouts occasionally.
General Motors and Samsung are also building in New Carlisle, a $3.5 billion EV battery plant begun in 2024. At Amazon, some 4,000 construction-related workers come to the site daily to make the speedy build-out possible. That's a lot for the roads around this 1,900-person town.
It's gotten very dangerous on Highway 20 and Highway 2, and the county has responded to that with more patrols. Our police department for our town has been taxed because they do respond also. That's the biggest concern, is safety.
Amazon is paying $7 million for highway improvements, and county officials told CNBC it's negotiating up to $15 million more for road improvements near the site. Amazon is also paying $114 million for upgrades to other utilities, like a water treatment plant and sewer lines. Although an AI data center is different, AWS has been building data centers for its millions of cloud computing customers for nearly 2 decades. And Infrastructure Services VP Prasad Kalyanaraman has been at Amazon that whole time. He sat down with Sigalos in Seattle.
When you want to build some capabilities for GenAI, which are unique to GenAI, like the network, or for instance, liquid cooling and so on, those are additions on top of foundational capabilities that we built over a long period of time. And that's what is unique about us, and that's why we're able to build at the scale that we are able to.
Speed and scale are key as Amazon joins the crowded race to build data centers for AI compute. Meta's 2-gigawatt Hyperion data center in Louisiana and OpenAI's 1-gigawatt Stargate site in Texas are 2 of the biggest that are being built now.
Many providers of that talk about gigawatts of capacity, but they don't tell you when they're going to get to gigawatt scale. What we have with Rainier is a real thing, which you've seen physically as well.
But what else sets Amazon's apart is it's filled entirely with its own in-house custom AI chips.
Behind me right now, they are working on delivering these towers. 2 of them together is going to make up 1 Ultra server. And inside of that is 64 AI chips. These are Amazon's own custom Trainium 2 chips. And what's especially interesting is there are no Nvidia GPUs in there.
Amazon's been designing its own chips since 2013, starting with a specialized chip called Nitro. It bought Israeli chip startup Annapurna Labs in 2015, where we got a tour. And by 2018, had its own ARM-based server chip, Graviton. Its first AI chip, Inferentia, came in 2019. Amazon launched Trainium 1 in 2021, and Trainium 2 came out last December. AWS chips have one main advantage: keeping down costs. Amazon CEO Andy Jassy said in July that Trainium 2 offers 30 to 40% better price performance than rival GPU instances.
Availability also, like there's massive backups for Nvidia chips, and if you can get chips faster and not have to wait online for Jensen to give you what you need, then you could get working faster and be in much better shape.
Trainium chips are less powerful and simpler than Nvidia GPUs. But Amazon says by fitting twice as many in each building, it can boost compute power and keep electricity and cooling needs down.
When you're able to control the stack all the way from the lowest layer of the infrastructure, you're able to build the right set of capabilities that these model providers want, right? You don't need to add all the other capabilities that you don't need.
Some say that Trainium 1 and Inferentia 2 instances haven't been as competitive for Gen AI training due to weak hardware specs or poor software integration. What do you say to those specific critiques?
Sure. I fully admit, Trainium 1, it was our first generation chip, and that absolutely was a learning chip, both from an architecture perspective as well as a software perspective. And Trainium 2, which is where we're at now, and then Trainium 3 is where we're quite excited about our cost competitive nature out there in the market.
Still, it's Google that remains the leader when it comes to these kinds of chips, known as custom ASICs, application-specific integrated circuits. Its tensor processing units, first announced in 2016, are used to power Google's own AI model, Gemini. And now Anthropic just announced its largest TPU deal to date with Google, giving Anthropic access to up to 1 million TPUs to train its LLM Claude.
There is such demand for our models that I think the only way we would have been able to serve as much as we've been able to serve so far this year is this multi-chip strategy, because new data centers are coming online. We're getting the capacity that we can wherever we can.
Amazon's taken a different approach. Instead of focusing on a flagship model of its own, it's invested some $8 billion in Anthropic as its key AI partner, and focused on its AWS Bedrock platform to support the development of others' models.
One of the things that's notable about the AWS partnership is we can bring that capacity into AWS Bedrock, where you have all the customers, they're ready to deploy, and they just need that capacity on top.
Founded in 2021 by former OpenAI researchers, Anthropic is focused on business clients and safety and security. Despite the recent Google deal, Anthropic has used AWS as its primary cloud provider, ever since Amazon's first big investment in Anthropic in 2023.
If you think about Anthropic, it really doesn't exist without Amazon. The multi-billion-dollar investments Amazon's made in the company is the reason why Anthropic is a player today.
You've seen this partnership evolve. Have you talked about buying Anthropic?
No, we love the partnership as it is.
The two worked hand in hand on the Indiana site and the chips inside.
They've given us good insights into what we need to accelerate in the chip, how we think about the various pieces of that chip that allow their models to train faster and more efficiently.
Developed alongside Anthropic, Trainium 3 is expected later this year.
It gives better performance, it gives better latency characteristics, it gives better power consumption per flop. And yes, that will be deployed inside of Indiana. It'll be deployed in many of our other data centers all around the world.
AWS and Anthropic are bringing the new site online during an unprecedented spending spree on AI compute, with more than $1 trillion in deals announced by OpenAI so far in 2025, among others.
Are you at all worried about these AI bubble fears?
Not for us in particular. I think others may have maybe more speculative investments on there or speculative deals.
I am not cashing any of the checks OpenAI is writing right now.
Concentrate fire on the target.
They are talking about a lot of data center capability and capacity. We don't know how the power is going to work to power these data centers. And a lot of what they're announcing is fairly speculative.
Turns out power is one of the reasons Indiana has become a hotbed for data center growth, with 7 new or proposed big tech data center sites reportedly in the works, from Microsoft, Meta, Google, and of course, Amazon.
We have a lot of fiber optic cable already. We kind of pride ourselves in Indiana as being an infrastructure hub, a highway corridor, railroads, transmission lines, gas pipelines, etc. We have that all here. But really also, it's the subsidies we have too.
Indiana's tax breaks for large data centers include an exemption from the state's 7% tax on electricity.
You'd think the appeal of attracting large big tech companies would be that they'd be paying taxes and contributing something to your economy. These big tech companies that can surely afford to pay their fair share are going to be getting a sweetheart deal.
The 2.2 gigawatt AWS site will consume as much electricity as 1.5 million of the average homes in I&M's service area. I&M will also power a new $2 billion Google data center it helped bring to Fort Wayne, Indiana.
The 2 data centers that we will serve will be almost as much as our entire electric load that we serve presently.
I&M anticipates peak power demand to more than double, from approximately 2.8 gigawatts in 2024 to more than 7 gigawatts by 2030.
So just that strong demand from data centers like Amazon is leading to market-wide price increases that are quite significant.
We have the capacity to provide this service. This isn't going to have an adverse impact on our existing customers. We are very diligent in the engineering and design of our system.
Still, one report found that monthly electricity bills in areas near new data centers are up to 267% higher than 5 years ago. 53% of I&M's power currently comes from a nearby nuclear plant, and 35% comes from a coal plant nearby that's slated for closure in 2028. Although the Trump administration said in September that most coal plants will delay retirement to deliver the power needed to fuel AI. Now, I&M is in the final stages of acquiring a natural gas plant in nearby Oregon, Ohio, that would make up 15% of the utility's power by the end of 2026. So how does that align with Amazon's pledge to reach net zero carbon emissions by 2040?
The path from here to 2040 is not going to be linear. Are there going to be needs for gas-based generation? I think there absolutely will be.
Amazon says it's also looking into small nuclear reactors and contributing clean energy to the Indiana grid.
We have over 5 wind and solar projects in Indiana for 635 megawatts of capacity that we actually supply to the grid already today.
As for water, Amazon says the data center is primarily cooled with outside air for all but 2% of the year. AWS wouldn't disclose how many millions of gallons the finished site will use, but said it's using on-site treatment to reduce water usage by 23% per year.
New Carlisle will supply the water to Amazon and then in the future GM that's going to build adjacent to Amazon. So that's a lot for a small town of 1,900 to take on.
Council President Marcy Kaufman told CNBC her town is doing an in-depth study of the local aquifers to figure out how to handle this project. Another issue, whether AWS will build on 10 acres of natural wetland in the middle of the project. Amazon told CNBC it's revising designs to minimize impact by the end of the year.
It's just going to be a constant fight for the data center builders to be able to build in these communities because for the amount of land and resources they use, they don't provide a ton of jobs.
Still, it's full speed ahead here, building out capacity for those million Trainium2 chips by the end of the year, and eventually Trainium3 chips in some of these buildings and beyond.
Because these buildings are there for like 30 or so years, and there's a ton of innovation that happens during that process. So it's a constantly evolving set of improvements that we do to our infrastructure all the time.
It doesn't look like it's going to slow down anytime soon. The money will keep coming until it doesn't, and it will probably take some form of economic downturn or a complete cessation of AI progress, which I don't see anytime in the near horizon to make this stop.
We're rapidly adding new capacity all over the place, and so I don't know that we'll be done ever. We're going to continue to build as our customers need more capacity.
Yeah, that was just a video I recently saw and I thought I shared with you. In the video, I think it was mentioned that Nvidia invested in OpenAI. I'm not sure if you have heard about that. Maybe a few weeks ago, the announcement was made. That's a prime example of how crazy the market is. And Nvidia announced to invest a very large sum, I don't remember how much, a very large sum into OpenAI so that OpenAI can buy the chips of Nvidia. And at the same time, then the stock price on Nvidia went up because it was considered positive news. The stock price went up by a larger number than Nvidia invested. So you could even argue Nvidia got a share of OpenAI for free or even made a profit by that. And of course, then the invested money will go back to Nvidia to buy their chips. So just an example, if you're a very large, powerful company, what's possible. I just decided that, it's okay if you come late here. I mean, it's not okay if you come late here, actually, but I can understand this at least. If you are online, I will just stop letting you in at like when the lecture begins. I just decided that in the future. So if you want to join, I should talk here to those people, not to you. So, and activate the camera. So if you want to join online, please be on time. I mean, you can even join the meeting room early, like 5 minutes early, 10 minutes early. You will just be let in automatically as soon as I start the lecture. But now let's start with the lecture, and let's start with linear regression and gradient descent. Linear regression is a very old technique, but gradient descent is also an old technique, but it's still being used today, and it explains to you very well how machine learning works. Just one other slide or a note before. In the first lecture, we talked about supervised and unsupervised learning. And I believe it was pretty clear what the difference is. Nowadays, with machine learning and things like large language models, it's not always so easy to distinguish. There's sometimes even discussions on Twitter or on some other channels where people discuss, are large language models and tools like ChatGPT, is it supervised or unsupervised learning? You see, he said language modeling is not unsupervised learning. And there's quite a discussion about this statement. I want to remind you about what we've been talking about last lecture. We will use this example in today's lecture as well, and in some of the future lectures too. We had this tabular data, a matrix with the students and their salary that they earned once they graduated. And we knew what how much time students spent, what the average marks are, and then we had the salary. And our goal was to predict the salary for a new student for whom we know the study time and the average marks. We talked about, I gave you this example, that we can represent this as a function, and we want to know, so we ignore now all those features, we just focus on one feature to make it very simple. We want to know what are the average marks. We know that the new student has an average mark of 2, and we want to predict the salary. And we see that as a function. F of 2 equals, well, we don't know. But we had the assumption that if we find a function that can predict f of 1 correctly, that can predict f of 3.7 correctly, that can predict f of 2.3 correctly, or at least not perfectly, but mostly correctly, then this function should also make the correct prediction for f equals 2. And I believe we discussed already that we will focus on a linear function. So a function like you see here in the blue line, in this example, just a straight line. And we want to fit the model. Now remember this terminology, fitting a model. That basically means a model is a function in this case. We want to find this function or the model that fits the data best. And fitting the data best simply means that the prediction error is lowest. We talk about that later. So, a second. So in this lecture, we will talk about how to find the best function. And again, a reminder, and you should look at that at home if you haven't done so already, you must know all this terminology. It's a bit difficult to, not really difficult to remember, but you must read it, you must memorize it. I will use this. There's sometimes many different words for the same thing. It's a bit confusing, possibly, but I'm sure you can learn this. So we talk about data sets. The data set is, at least in all our examples, tabular data, which can be seen as a table or a matrix. So this here is a data set, all of this. Each row in a data set is an instance, so let's say one student or one house. Each column represents the features, so like the time the student spent or the average marks. So to show this one moment. So that's all the same, the red things. This is the visualization. It is easy to understand. We see that as a matrix without the last, typically the last column, which are the labels. It's not a natural law. The label is not always necessarily the last column in a data set. Of course, you could also, if you knew the average salary, you could also try to predict if you knew the salary of a student, you could also predict the average marks that the student has. Or you can choose almost any column you want in a data set as the label. It's just what you want to predict. It depends on your application scenario. And we represent this as a vector. The label here, that's typically the last column in your data set. We call it the vector y, with the labels 1 to m. There are m instances in your data set and consequently m labels in your data set. We represent this matrix as a collection of vectors. So this bold x1 vector is nothing but all these elements in the first row. And then, or just to show this, yeah, that's the same here. And then the vector xi is just the ith row in m here. I use two different notations, sometimes the normal, the standard vector notation here, and sometimes the transposed vector I sometimes write it like this and don't write the t here. It should always be self-explaining. And like for the understanding, it doesn't really matter in which way I'm writing it. It's only later for the calculations important. Okay. If I'm too fast or you have questions, just raise your hand. Yeah, I'm happy to explain things more. Let's talk about the formal, or let's talk about the goal informally. And let's take a new simple example. We have a very simple data set with those instances, 1 to 4. They just have a single feature. Each instance has one single feature. So this year's instance, so I should have put some ID here maybe to make it more clear. This is instance 1, instance 2, instance 3, instance 4, and they have the values 1, 2, 4, 5. And these are the labels. And we want to predict y for any given x1. So for some new instance 1, or for some new instance 2, or some new instance e. These are the features of the new instances. We want to predict y. And the assumption is that, and it's a new term again, we have a hypothesis that's again the same as a model or a function that is modeling our data. So we will look at linear functions. In theory, there's a perfect model for anything. So whatever your data points are, you could find a mathematical function that is modeling all of them, even if it would look like this, as long as there's not 2 points with the same x value and different y values, you could find a perfect function. Now, just to this, in this example, the model that would predict all values correctly is this function. So, and like if you wanted to make a prediction for, let's say, for 2, you just take the 2 and plug it into the x. Here, 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 and here. And then you would get exactly the right value, 3.25. You can see it. That's here. So in theory, this is what we want to find in this example, this function. Automatically, we want to find that. I mean, I'm giving it to you now because I just created it. But when we talk about machine learning, what you have is only the points. Only this you have. And then you want to find this. Yeah, now you need to find the function to make predictions. If you had this function, now you could make predictions for this. And if you put the 3 in here and here and here and here, you would have the right value. But it's extremely difficult to do that. And also, if you will learn about it later, you would in practice not get good results. You would overfit your data. You will learn later what that means. So we are looking at the linear problem, and a linear problem in a one-dimensional space is very simply defined. You know that the straight line is defined as mx plus b. So that's what we want to find. A simple linear model or function, mx plus b, that is as good as possible. It's an optimization problem. If you continue some lectures on machine learning, you will hear this term as well very often, an optimization problem. It's not just to find the right model, it's also to find the right hyperparameter and other things. And an optimization problem means there's a very large number of potential answers, and finding the optimum is typically non-trivial. The optimal function is that function where the error of the prediction is lowest. So if you were to randomly start with this function, you could see already it's quite far off, because if you somehow came up with this function, then you would make a prediction for number 1, you would make this prediction, but you know based on your data set that this is the true value. And you would make a prediction for x1 equals 2, and your prediction based on this formula, 1/2 multiplied by 2 is 1. So I plotted this wrong, I think. This should be here. Oh, no, sorry. No, it's right, of course. Yeah, it's right. So your prediction would be here, but you know from your data set, the actual value is this. If you now come up with a different function, you can see already it's better in terms of like this error is smaller than this error, and so on. If you sum up all the errors, the green function clearly would be better than the yellow function. And for now, we just take the simple difference between the prediction and the actual value. So this is the prediction, and that is the actual value. And the difference is your error. And the sum of all your errors tell you how good the model works in total. To put this a bit more formally, we are looking for a model that is mapping the input vector xi to its label yi. And the assumption is, if you can predict the existing values, that's why it's called supervised learning, if you can predict the existing values well, we will be able to predict unknown values well as well. So the big difference here is compared to standard problem solving with the computer. Typically, you have here your input and you have your output, and then you craft with your hands a rule or an algorithm that is doing the mapping, that is sorting something, that is deciding if someone likes a cake, if you remember from the first example, from the first lecture. And now in machine learning, this model or function is automatically created by a machine learning algorithm. In this case, linear regression, but there's many algorithms. That is based on this data, learning this. Now, how can we do that? How would you do that? I'm telling you, and there's an n-dimensional space. Yeah? We now look at this 1- or 2-dimensional space. But in practice, you have a large data set with many features, so it would be an n-dimensional space. How can you automatically find the best straight line here? And maybe the question is to those people who have not attended the CIS lecture. Yeah. Yeah, so you really know the right answer already, right? From you did some online course or something, it's right. But the question to those of you who have not attended any machine learning lecture before, I hope there's at least a few here. How would you do it? Or even forget about what you have learned. That's your task now. Create an algorithm that can find this automatically. How would you do that? Yeah. Maybe change the slope intercept and then change what the algorithm is by studying then continue until you have until you yeah. I think it's so you would take a random function, right? And then you would take a second, or then you would change the slope or the intercept somehow. But how exactly to do that is really not trivial. I showed some of you know the answer already. I will show you the solution now, and it's really simple, but not easy to come up with. It's quite pretty, I have to say, in terms of mathematically, because it's so simple and yet so powerful. So the approach I'm showing to you is called batch gradient descent. It's being used for linear regression to find this linear model, but it's also used for neural networks. And neural networks are being used for large language models. Or large language models are a very particular kind of a neural network. And gradient descent is used for many variations of that. Or in general, it's used to solve many optimization problems. So now you need to listen closely. This is an important step. We start with this. Our hypothesis, or the function, is the very simple function that you know from high school for a straight line, mx plus b. What is the equivalent function for n dimensions or for n variables? The linear function in an n-dimensional space. I'm not sure if do you know this? I mean, I'm not sure if you. I did not have this in high school. I believe. Did you have that in some other math lectures? Like,
I mean, it doesn't have a specific name.
Yeah, but there's a name for n equals 3. But like the formula, how does this look like? How does this look like if you have right now here you only have a single variable in your data set? That would be the time the student studies, for instance. And m and b are just, well, parameters of your function. Yeah. Yeah. So this would be the generic form with n variables. You basically have the same. So b remains here. And then you have mx for each of your variables. So mx1 or m1x1, m2x2. And this would be your first variable in the data set, the study time, the second variable in your data set, the average marks, and another variable, and another variable. Each variable has this factor m that is weighting it. And then you have a linear model in an n-dimensional space. Like either have a straight line or a plane. But with this function, you cannot really easily work. And you cannot find that automatically, the best one. So I will show you, but first you think about this. How can you come from this function to here? I will show you in the next slides how you can easily optimize and find the optimal parameters and functions here. So somehow there's a way to come up from this function to this vector and this vector. Anyways, who of you has attended my CIS lecture? The Complex and Intelligent Systems lecture. Like if you are not sure, then you have not attended it.
Oh,
Ah, okay, sorry. Okay, so not all of you. Good. So the people who attended the lecture already know the answer, but probably have forgotten the way. So I think about this for 2 or 3 minutes. Talk with your neighbor. Practice your math skills. It's very simple. It's not high-level math. It's just replacing some letters and compressing them into a compact form and then converting them to a vector. How can you come from here to here? Yeah. Sorry?
Minimize the.
Yeah, let's wait 2 minutes or so everyone can think about it. One moment. I will just show it to you. But if you are watching this as a video, it's a good practice to really think about that. So we just change the notation and order. We replace B with theta 0, and we replace each M with theta, and then the corresponding index. So that gives us this formula, theta 0 plus theta 1 x1, theta 2 x2, and so on and so forth. In the next step, we just write it a bit more compact and use the sum of this. So we keep theta 0 here. But here, the sum of the products can just be rewritten as here. The sum from j equals 1 to n. So for all instances, you just sum up theta j times xj. And if we now define x0 as 1, we can also move this into the sum function. So just look at carefully. Here we have j equals 1. So that's everything starting from here to the end. If we define x0 as 1 and basically put x0 here, so theta 0 times x0, then we can also move this into the sum. And then we come up with this. So the good thing here is we lost B. We have, or like we integrated it. We did not really lose it. We integrated it into the other part. So we have transformed now this formula into this compact way. And this is nothing else but as a vector, this. If you multiply those two vectors, you will get again this or this. The red boxes are the most important parts to remember. Also important to remember that theta 0 or B is sometimes called bias. Yeah. Is that clear so far? Yeah. So, okay. Now we have a vector. Okay. What does this vector really mean in terms of our data set? This here is our data set with the labels where we have all the x's, all the values of the variables. And we want to predict them. We want to predict the label. So what we want is that if we now incorporate the theta 0 is basically a new column here in front of the data set. This is our value that we have, x1, xj, study time, average marks. And we want that if we are weighting our existing values in the data set with theta 1 or theta j here or theta n, and then sum up all the values, the weighted values, we get y. And the challenge is that theta 1 here is the same for all instances. We want to have one theta 1 that we can use to weight this value, and this value. And we want one theta j that we can use to weight this value, and this value. And then if we build the sum here, it should be this y. If we build the weighted sum here, it should be this value. And it's probably pretty clear that we can never find a theta 1 or a theta 2 so that in the end we always have perfect predictions. So again, I'm repeating myself, we just want to have good enough predictions. And X is given, the data set is given, the right values, and Y is also given. So the only thing we can change is theta. All those thetas that are weighting our input vectors. And that is what we want to find, the optimal theta. When we find that, when we find theta, the vector, so all the individual thetas, theta 0, theta 1, theta 2, then we can make predictions. And if those predictions are close to y, we are finished. That's our goal. So we have now broken down the main problem to an optimization problem in finding the vector theta. And this is how you do it. That is the solution. That's the algorithm called gradient descent or batch gradient descent that is giving you the best possible theta, so the best possible weight for each of your input variables, values. So let's look at that closely. You start by initializing theta randomly. So all values in this vector you initialize randomly with very small numbers. And then for each theta, you just update it until the stopping criteria is met. Stopping criteria is met means, well, ideally the error is 0, which again, as I said, will normally never happen, or until the error is small enough, whatever you define as small enough, or until the time is up. So you say, I just have 1 hour, so compute as long until the 1 hour is over, or a week, or a month, or until the error doesn't change anymore. That's maybe the normal stopping criteria. You run your learning, or you run this iterative process until the error remains stable, more or less. So look at this carefully. For each theta j, you are setting its new value to the old value minus alpha. Alpha is just a small constant number multiplied by the sum of the error multiplied by xj. So xj is your value, your feature, study time for a particular instance, multiplied with the error for that particular instance. You do that for all m instances. So what you do, for each instance in your data set, you take your first instance in the data set, you make a prediction with your random weights. Camera off, sorry. You make a prediction. Once you have the prediction, you can calculate the error, so just the difference between your predicted value and the actual value, and you multiply that error with the xj, that is, let's say, the study time for which you are looking to find the optimal theta j. Yeah, so keep in mind the error, so E is nothing but the predicted value minus the actual value. And the predicted value is nothing but this linear function that we just had. Just the weighted sum of all your values. So, and that's it. That is machine learning. You probably have not yet understood by now how great that is. So, because probably you will not think, wow, that's a really cool formula. Really pretty, really beautiful. Because it's not intuitive, I would say. If you look at this, I mean, I will show you on the next slide that it works. The big question is, why does it work? And we will talk that. We will talk about that as well. So let me show to you first now that this formula works. And after that, we talk about why it works and why it works generically for any data set. And yeah.
Once again, what's stopping criteria?
The stopping criteria is like your definition when you want to stop. So either you say, I want to stop when the error is 0, or when the error is small enough, whatever you define as small enough. So, or when you say, tomorrow you have to submit your bachelor thesis. I only have 3 hours left. So let this run for 3 hours, and whatever I have, stop it. Or if the error doesn't change. Okay. So let's look at an example. This is your data set, the red box. That is what you will be working in the lab sessions with. This is what you're working in a company. Of course, in a company and even the lab sessions, you have much more X. You have not just one variable, you have dozens or hundreds or even thousands of variables. You normally have just one Y, one label. So that's given. The left part here, that is hypothetical, or that is part of your model, but it's not given. I've provided it here because I made this example up to calculate Y. So I was sitting down, just taking a calculator to make a perfect example in which I said, okay, based on our definition here, we have our model. So if you have one variable in your data set, you will have 2 variables in your model, M and B. If there were 2 variables given in your data set, you would have 3 variables in your model. You would have X1, X2, and B again. Or we are not using the term B anymore. We say X0 and theta 0 as the weighting factor. So as I said before, X0 by definition is always 1. What we want to find is theta 0 and theta 1. So that if you calculate 0.5 multiplied by 1 plus 1.5 multiplied by 1 equals 2. And the same here, 0.5 times 1 plus 1.5 times 2 equals 3.5. So we can calculate already, because we have the information, 0.5 times 1 plus 0.5 times 1 plus 1.5 times 3, and whatever the result is would be a prediction for this. Now, I've given this to you already. The point is you don't have that normally. So we must find this. And now remember again the algorithm that I just showed to you. We start with random numbers. We initialize theta 0 and theta 1 with random small numbers. For instance, this or this. Now we make a prediction. So we calculate 0.02 times 1 plus 0.01 times 1 equals 0.03. That is our prediction. So the difference between predicted value and actual value is minus 1.97. We do the same for the second instance and for the third instance. Later we will look at the squared error here as well. Sorry. Yeah. So let me see. Yeah. So these are the real data points, the actual data points. And this is our model that we have, the initial model. Yeah, just the model based on this and this. So the function 0.02 times x0 plus this times this is just this. And now we are updating our values. Update 1. So this is the value from before, from the slide before, that we have randomly chosen. We have randomly chosen this. And now we use this formula to update this. E, we already calculated on the previous slides. That was here. So the difference between actual and predicted value. E times xj is here. So this multiplied by this is minus 1.97. This, sorry, so this times this is this. This times this is this, so it's the same. But here, to calculate this value, this multiplied by this. And to calculate this value, we take this multiplied by 2. It's just the error multiplied by the corresponding x. And now we just put in the numbers and calculate the update. So the new theta 0 is set to the old value, that is here, 0.02, minus alpha. Alpha is just given. It's called a hyperparameter. It's just a small value. How you determine this small value, we will talk about later, but it's a constant number that is used for scaling. So multiplied by the sum of this. So the sum here, if you sum up those three values, you get 11 minus 11.87. That's here. So this is the new value of theta 0. And you do the same for theta 1 and you get this. And now you have a new model. This is your new model, theta 0 and theta 1. And here's the plot of the new model. And you can see already it's better, much better. So if you now apply the same, let's look at this. That was the first iteration. That was the initial iteration, the initial run, the first run. The next one would look like this. Next one like this, then like this. So almost perfect. It's not perfect, but it's almost perfect. After 100 iterations, it would look like this. So you remember, I used 0.5 and 1.5 to calculate this. So those would be the perfect values. And we are very close to the perfect values. And this works for basically any data set. Yeah?
Is it possible for the algorithm getting worse?
No, well, it could be that you are jumping over the optimal solution. So, I mean, right now it became better and better and better and better. It could be that the next line would be here, maybe. And after that, you go again towards this. It could not happen that your first iteration, so you're starting randomly, right? Whatever, like here. It could not happen that the next step would be worse. Every step is getting better. And if for some reason you're jumping over the optimal solution, after that, you again jump closer to the perfect solution.
So a large time frame with iteration.
Correct. Yeah. That's the beauty of this formula, that if you look at it, the better your solution, the lower is the error. And the lower the error, the lower the update. If you think about, if you would have a perfect solution, then this whole term would be 0, right? So then your update would just be alpha. So in theory, you could get worse one time, and that would be if you hit the perfect solution, you do a new iteration, and then you decrease your performance by alpha. So in theory, that could happen. Yeah. Yeah.
But the alpha is 0 because the other is 2.
Oh, yeah, you are absolutely right. Yeah. So yeah, you can really never, yeah, exactly. We can skip this. Okay. Yeah.
If you make alpha lower, maybe be more precise.
Okay, let's talk about alpha again. Why do we have alpha in the first place?
Makes it smaller.
It makes the steps smaller. Why? Why is that necessary?
Governs how big is the change in the error.
Yes, and if you think about what values you may have here, they may be reasonably large, right? Think about house prices. If you want to predict house prices, you may be off by 10,000 or 50,000, and the variable you have, so x0, xj, may also be quite high. So that would be a quite large number. So that means the update of the weight would be very large, possibly too large. So you would always be jumping back and forth. So you raised your hand?
If the number to update each iteration is too large, you could end up in a situation where you're bouncing around the optimum, but not.
Yeah. So you could always bounce around the optimum. So you want a small alpha so that the updates are not too big. You don't want to have a tiny alpha, because then the steps, the updates would be very small and you need a long time to find the optimum. Okay. So very simple formula. This is gradient descent. This is still a core of the most modern machine learning algorithms to find an optimum. Just to make this clear, so we are now looking at 1 or 2 or 3 variables in your data set. And you have maybe heard of ChatGPT, that the model of ChatGPT has billions or trillions of parameters. What that means is they have billions of xj's for which you need to find a weight. Not all as an input. So here we just have this one input. Later we will talk about that as well. When we talk about neural networks, we have your input, let's say 10 variables, 10 different x's, so x1 to x10. You are weighting them, and then the output of that is going to the next layer, where you again have maybe 10 or 20 x, all with their individual weights. But in principle, the modern neural networks still follow this. They have many parameters. This is a parameter, an x, and they have for each parameter a weight. And the challenge for ChatGPT and so on is to find these billions of parameters so that the output is what it should be. Okay, now, why this formula? How could you possibly come up with this? Now you remember we had the simple sum formula of the hypothesis, just the weighted sum. How can you now come up with the idea that you must update each theta like this? And this is a really, yeah, I will show it to you. And I think I would not have been able to come up with this idea, even though it's so simple. But if you ever have a similar idea, you will become famous. So for now, forget this formula. And just think about, what do we want to do? We want to optimize our error. We want to minimize the sum of all our errors. Now we want to, and we call this a cost function. Also a popular term in machine learning. A cost function, I don't know why they call it cost function. It just measures how good your model is. Not always with errors. There's also other ways of measuring this, but for now, just consider the sum of errors, an error function. But we are not using what we have been using so far, just the difference of the predicted and the actual value, we are using as the cost function the square of the error. So the predicted value minus the actual value, and we square it, and then we sum up all those values, and we divide it by 2 in this example. We divide it by 2 because that will make the calculation later easy. In practice, this is often 1 divided by m. Sometimes 1 divided by 2m. Do you have an idea why that might be good? Why do you maybe want to divide this by m? Do you have any idea? The students were talking the whole time. Yes. Do you have an idea? No. Anyone else? You.
And you want to average error for each instance.
Yeah. It's not absolutely necessary to do that, but it is scaling the error so that regardless of how many instances you have, you always have the similar value here, like the same proportion. Okay. So it becomes clear later why this must be squared. You cannot use this without squaring it. Yeah, we will go through that together. Just another example. Okay, let me explain this to you. Again, the same data set as before. X1 and Y is given. And then the hypothetical X0 that we define as 1. And now we try out different thetas to see what happens. So we set, to make it easy, we set theta 0 just to 0. And we will try out different theta 1s. We try out 0, 0.5, 1, 1.5, 2, and 2.5. If we do that, we will get these results here. Now you can calculate it at home to see if I did a mistake. Or these are the charts, the plots, the functions. And you see already that the red function probably is the best. Now we calculate the error. So the errors is just the difference between predicted and actual value, and the cost function, and that's also important in the exam. Don't forget that to use the cost function is not just the sum of the errors, it's the squared sum. So it's easy to forget that. It's easy to forget that, and then you will get a wrong result here. Again, calculate this out. Just if you square this plus square this plus square this plus square this, you should, and then half, take half of it, don't forget that, divide it by a half, and then you should get this. If we plot this, we will get this chart. What this means, and this is really important, this is plotting the costs here, the costs versus changing one of your parameters. Remember, we have many parameters typically. We have theta 0, we have theta 1, we have theta 2. Here we just look at one parameter. So if, well, you see already the optimal parameter is somewhere here. So we start here, we go here, we go here, we go here. That's the optimum that we want to find of the given values. The theoretical optimum would be here. So how do, I mean, now we could just calculate all these things, try out random thetas, and look what's the lowest error value. But if you want to do this more structured, how can you find the lowest possible value here? So we have plotted this function, and we want to know where the optimal value lies. Think about this. The solution is really easy. Every one of you knows the solution from high school. Yeah. Yeah, you build a derivative of the function. I mean, I don't know about your high school time, but between grade 10 and 13, that's what we did all the time. And I never understood why we do that. Why would you want to calculate the minimum of a function? Who needs this? Now I know, and now you know, or in a few minutes you will really know. You can use it to find the lowest point of this cost function. And that's what you want to do. You want to know where is this where is this equaling 0, or at least the lowest point. Yeah, the error is not always 0. It can be higher, but your goal is to find the lowest possible point, the minimum. So if you build a derivative of this, you should find this point. And you will come across many cost functions if you continue some other lectures. Remember, if a cost function is convex, you can always build a derivative and you find the optimal solution. So the main idea here is start with a random point. Update the point, go here and here and here. Maybe you will jump over the optimum and then go back. Or if you have two variables, which you always have, at least, yeah, this is the weight for the one instance in your data, for the one feature in your data set, and that is for this bias. It would look like this. It's a plane in the space, and you would start somewhere and you go down, 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 and at some point you would end up here. So just, just as a, like if you were completely new to this field and you want to find a solution, this would be hopefully your thinking steps. You just start with random parameters and you modify the thetas so that J is reduced. So how do we do this? How do you know that you need to increase or decrease theta? And how much do you need to increase or decrease it? And how do you know to stop? And you mentioned it already. We take the derivative or the gradient. And it's fine. We don't even, well, that's basically automatically. So we build the derivative to get the gradient, and we just take the gradient as an update. If you build the derivative of this function here, you will get a gradient that tells you how steep the function is at this place. So what's the consequence? What's the gradient here? Is it positive or negative? Negative. Yeah. What's the gradient here? Positive. So if you take the gradient, you have already, so the gradient tells you in which direction to go, basically to find the optimum, the maximum or the minimum, depending on the sign. So you can use that already to decide, should you increase or decrease your function. And then where's the gradient larger? Is it larger here or is it larger here? It's larger here, right? So here you have a relatively large gradient. Here you have a relatively low gradient. So if you take your original theta and you multiply or you add or subtract your gradient, the update will be larger if you do an update here and will be smaller here. And that's what you want. I mean, if you are here, it's very steep. so you know you are quite far off the optimum. So you can do a big update. If you are here, the gradient is low. So you know already, oh, you are quite close to the optimum. So you don't want to have a very large step in the update, because then you might jump over the perfect solution. So the gradient is really nice. It tells you automatically if to increase or decrease theta, and it's smaller or larger depending on how close you are to the optimum. So, sorry. So the intuition here is basically take your existing theta and then, well, subtract or add or multiply it with the gradient. And that will give you a good update in the right direction and the right size. So, and then when to stop. So that's what. So should you increase or decrease the individual parameters? The gradient will tell you. How much to increase or decrease? Again, the gradient will tell you, or the update formula. And when to stop? That's what we just talked about. That's the stopping criteria. Yeah, we had that already. So when we talk about the gradient, I'm not sure about your high school education. We typically had one or a maximum of two variables, I believe. So if you have a multivariable function, which we have now all the time in machine learning, so we have multiple input variables x, then the gradient consists of the partial derivatives of all the individual functions. So the gradient is a vector of all the functions' partial derivatives. And the gradient or the partial derivatives tell you if you had one point in the vector space, in which direction should you go to increase your values best. But we don't want to increase it, we want to decrease it. So that's why we are subtracting the result we get from theta. I think we will skip that. Keep in mind, we are here talking all the time about simple cost functions with a global optimum. A global optimum means it's a global minima. So the cost function has just one minima, which is also the best and only minima. There are cost functions that maybe look like this or this. So if you were to start with typical gradient descent, you would come here and think, oh, I'm finished. But if you were to continue, you would maybe find the global optimum here. How to identify that and when this happens is beyond the scope of this lecture, but keep it in mind. We are looking at simple examples where there's always just one optima, which is then, of course, by definition, the global optimum. So coming back to this question, why does the update formula work? Here, that's the update formula again. Why does it work? The intuition is this. The new theta is set to the value of the old theta minus, again, the learning rate is just for scaling, minus the partial derivative of the cost function. So that is telling you basically in which direction to go to get the maximum. We don't want the maximum, we want to go in the opposite direction. So that's why we are subtracting the value. And this is telling you in the simple example, it's telling you the slope of the function, and the same basically in a multi-dimensional space. So how can we come from here to here? And that's really the challenge. Like, imagine that this wouldn't exist, what I'm teaching to you. Like the first person who came up with this, it's already quite an achievement, quite clever to come up with this idea that you just use the gradient instead of maybe some hard-coded rule to try out this and then try out that. And if the value is bigger than this, then maybe try this. This is a really elegant method. And then the next challenge is, once you have this idea, how can you come to this simple update formula? And that's what we go through now. So, let me look at this myself. It's a while ago. Okay, that's our intuition. And we focus only on this part for now, the partial derivative of the cost function with respect to every theta that is in the cost function. Again, just as a reminder, theta j is the weight of your variables that are given in the data set. And those thetas are the only thing we can change. So maybe you also still remember that the partial derivative of a sum is the same as the sum of the partial of the derivatives. So we can rewrite this as this. This is our cost function that I just gave to you. It's a cost function. So we take the partial derivative. So it's just rewritten here. And now remember the partial derivative of a sum is the same as the sum of the partial derivatives. And we cannot really calculate with this y hat, but you maybe also remember I told you y hat is the predicted value, and the predicted value is nothing else but the hypothesis or the function that you have. And we ignore the sum for now. We ignore this. We focus on this. We cannot calculate with this, so we replace y hat with h theta. And here, h theta, again, not perfect to use, to calculate with. So, oh no, sorry. Now we first apply the chain rule. So we have here, we want to build the partial derivative of the square of this. So we apply the chain rule to get this result. For those who are not remembering exactly the chain rule, what you do is basically you take this 2, it comes here. We keep this expression, it remains here. That's exactly still the same. And we multiply it with the partial derivative of this, but without the square. And now we can make this a bit nicer. Here, 2 times a half just becomes 1. So that's why we had 1/2 in the cost function. No? Why we have a half here, it just makes it a bit nicer and easier. So what we keep is this. This expression just remains for now here. And now what I just said, we cannot calculate directly with h, with the hypothesis. So we use really the, let's say, the final formula for this, or the individual parts, which is just the weighted sum. That's clear, I hope, that h of x is just this whole expression up to here. And we keep y here. Y is the label it's given. It's just a number typically in the data set. Do you follow me? So if not, watch this video at home. This is like really important for the understanding how you come from here to here. And now we build the partial derivative of this whole expression with respect to theta j. What is the partial derivative of this with respect to j, with respect to theta j? I know you know the answer because you attended previous lectures of mine. I remember you. You always talk. So what's the right answer? That's the partial derivative. Here. don't know the answer. It's really simple.
It isn't.
But think about it. You know this from high school. Really, you raise a hand. It's XJ. Yes, it's J. XJ. Yeah, that's the right answer. I hope you remember this from high school. If not, you should make it fresh up your knowledge on this. The only thing that matters here is that term that contains theta j. Everything else doesn't matter. So if you build the derivative of this, just the so in German, die ganz normale Ableitung from this expression, and you assume that xj is what you always know as x in high school, then only, sorry, with theta j, so then only xj remains. Everything else is just considered a constant number and vanishes. So the partial derivative of this whole expression just is this. And this is nice. Now we are rid of this partial derivative expression. We only have xj here, and we still have this expression. So, and this is something we can calculate with, because if you remember, that is the predicted value minus the actual value, and that is just e. So now we can go back and replace this with e. We keep this here. We take back the sum sign that we could ignore so far, and alpha is just the scaling constant anyway. So this is linear regression, basically. Someone someday came up with this intuition, and I hope that if you see this formula, you would say, "Oh yeah, I understand, and this makes sense." You want to find the minimum, and you have these requirements that you don't know in which direction to go, like if you should increase or decrease theta, and you don't know how much to increase or decrease theta. And the gradient is just giving you a perfect answer to that in combination with alpha, the scaling factor. So, and then from this, if you continue, you come up with this update formula that's just very easy to calculate. You don't need, like any computer, your mobile phone can do that easily. So here again, the algorithm, gradient descent for linear, not for linear, so it's gradient descent. Initialize theta randomly, and then do this until your stopping criteria is met. Here the intuition, here the actual formula that you can use to calculate something. Any questions so far? It's really important that you understand like every step that I showed to you. If you have questions or if there's something that's yet unclear, watch the video at home. It's also really important for one of the last lectures when we talk about neural networks. There's a few assumptions of, yeah?
But the model can only be as good as the data that you use to train.
Yeah.
Beginning, you have the example of the grades and study providing the diagrams.
Yeah.
Doesn't correlate.
Absolutely. Your model can only be as good as the data that you have. And we talk about that in a future lecture as well. There's a nice saying in machine learning, garbage in, garbage out. If you have bad data, well, then it's just impossible to have a good model. I mean, yeah.
Question for you is, we're talking about examples to the definitions. We're talking about billions of. How do I know inputting that's getting assumptions that seed right, I cannot always.
Yeah. Sorry. Can we remove the question?
Yeah, more data to explode. has to correlate, otherwise there will be wrong assumptions calculated. Data points. They have what we today correlate.
Well, okay, so talking about LLMs with possibly billions of parameters, they somehow the input does correlate to the output. Now it's not as easy as here. Also, let's back to the slide from Twitter I showed you. LLMs are not that clearly supervised learning. It's not that you have one input and you know exactly what the output should be. Yeah, you remember last lecture I showed you the examples with images as well. If you generate an image with a neural network, it's not exactly supervised learning. It's not that you have a label. It's not that you say you want an input string cat, and this is exactly the image that should be given out. This is an infinitive number of images that could be generated that show a cat and that are good, perfect outputs. The same as an LLM. There's an infinitive number of valid outputs. Some are better, some are worse. But back to your question, I mean, that's kind of the magic of deep learning, of large language models, of neural networks, that, yeah, there is some kind of, like we call it, correlation between the input and the output. And of course, if you have a model with billions of parameters, you cannot just have 1,000 training instances. To train billions of parameters, you need billions, trillions, I don't know what the next number is, of training instances. That's why large language models are trained on basically the entire internet and more. And that's why it's so valuable to have unique training data. That's why the data that Google has on YouTube, or possibly, I don't think they use Gmail, but who knows in the future, or what Elon Musk has with Twitter, that is unique data that only they have the right to use, or newspapers with their gigantic archives collected through the last 100 years. And that is why the AI companies pay billions of dollars to get access to that data, because you need it to train these gigantic models. But yes, in the end, in the principle, it's the same like this. You train and you train and you train for a month your large language models to find all those parameters theta, and then quite a bit around there. But okay. Basic assumption of linear regression is there is a linear, and maybe that's back to your question. The basic assumption is there must be a linear relationship between X and Y, so between the input and the output. There must be, you call it a correlation, or like I call it here, a linear relationship. And then with more complex models, it's not a linear relationship anymore. But there's some relationship. Of course, also with any normal real world data, there is no strict linear relationship. It hardly ever happens. So we need a second assumption just to make this first assumption true. And that is there's some noise in the data. And that clearly is a true assumption. So your real function or your model is not just theta times X. It's this expression plus some noise. And we talk about noise in one of the future lectures. And so this would explain then deviations. Yeah, this is also important. And every year, actually every semester, I tell students this is really important. Listen carefully. And every year, many students do it wrong in the exam. So listen carefully. There's different metrics for linear regression and gradient descent. Just now, we talked about the cost function. That is about measuring directly the training process of linear regression. So, and this is the cost function. And it must be this way, it must be squared, because you can only build the derivative and take the gradient of a function that is, you can't take the derivative is not defined, or it's zero, or not defined. of this. If you take the square, then you can build the derivative and optimize it with gradient descent. It's something called least square optimization, or it's called the mean squared error. Yeah, this is not used by humans typically. It's just, it must be like this so that gradient descent works. What humans use, or if you write your bachelor thesis and then you want to express how good a model works so that everyone understands that, you typically just use the mean absolute error. That is what every person in the world without any computer science background would understand as an average error. If you predict house prices and you would tell your grandparents, oh, I can predict the house price with a mean absolute error of 10,000, they would probably understand that typically your prediction is around 10,000 off on average. So that's the most intuitive error for humans. That is what you should maybe report in your bachelor thesis or master thesis, what you would use in your daily life. Then a very common other metric is the root mean square error. It's basically the same like this, only that you square it. So it's basically the same like this, but you divide it by m. So that is still basically the same like this, but you take the square root as well. Yeah.
So the reason why we use for this algorithm the mean square error is it's easier to calculate.
Yeah.
So the theory was used to be error, but then the formula is way more.
I'm not sure if can you repeat?
So my question is, why, for example, we don't use the mean absolute error for our custom.
Because we cannot build a derivative from this.
Absolutely.
Yeah. So the whole assumption that I took today was you need a cost function where you can build the derivative so that you have a gradient and can use that to change theta. And the gradient gives you direction and the how big the update should be. So that's only possible with a cost function where you can build the derivative. You cannot build the derivative here, or if it's one, then so it's not useful. So why would, and this is very common as well, root mean square error. So it's basically this, but then the square root, or you could argue it's also like this, but you square it and the average and then the square root. Why would people, and again, this and this are metrics people report in their scientific publications, in their bachelor thesis, if they talk to colleagues. They talk about this and this. This is something they only use to find the optimal function, like their optimal linear model. I think this is very intuitive. Why would anyone use this?
Large errors and effectively, and it's not be as big of an effect when we have individual function individual bound or.
But it's rather the opposite, right? So if you depending on what you compare it. So the question is rather, why would you use this and not this? I mean, there's no reason really to use this. Well, debatable, but typically the decision is, should you use this or this in your report? Or that you say, okay, I want to recommend a system, or I want machine learning prediction that has like a good result here or here. If you are squaring the differences, this has a stronger effect on the overall metric. So let's say you have two algorithms one algorithm makes a few really bad predictions and many really good predictions. So you have a few large errors and many very small errors. And then you have a second algorithm that makes constantly average high errors. Then this formula would punish the first algorithm that makes a few very large errors. Now, if you square those large numbers, they become even larger. And if you then build the average and only after that take the square root, then the error is larger than with this formula. So if for some reason you want a system, and that there's no right or wrong here, it depends on your application scenario. If you operate the system, if you run a business and you say, I want to avoid large errors, so I'd rather have a system that makes constantly some errors, but that's to prefer it over a system that is often like really good, but sometimes like super, super bad, then you would use the root mean square error. Or you just use both metrics and look at both of them. Almost always, it's not a big difference in practice, but yeah, you should be aware of the differences. Okay, I wrote here that was your first real machine learning algorithm. What was your other first machine learning algorithm? Last lecture, you remember? Yeah, KNN. So last lecture you learned about KNN, and I said already, it's not, in my opinion, it's not really a machine learning algorithm, because what you saw today, in my understanding, is real machine learning. You create a model. You have an algorithm that creates kind of another algorithm, this function. You have the linear regression algorithm that's creating the linear model. And this linear model is nothing but a mathematical function that you can use to make your predictions. There's many extensions to this. So you learned today about batch gradient descent. Batch gradient descent just says you look at your entire data set, then you update your weights. You can also do stochastic or mini batch gradient descent. So you do an update after every iteration, after every instance, or just take mini batches. So let's say 10 or 100 or 1,000 instances. Use them and update your weights. I'm not sure if you are aware of that. Maybe you've learned of that before. For linear, linear regression is extremely old in psychology and wherever it's been used since long, long time. And they have not been using gradient descent to find a linear function to match their data. They're using something called the normal equation or closed form solution. If you have data points with a relatively small number of variables, a few dozens, I think, no problem, there's some other formula that is giving you the right perfect model basically right away. So that is then to prefer over gradient descent, where it takes many iterations and possibly still not giving you the exact perfect solution. But with large data sets or many variables, gradient descent is to prefer. And again, with linear regression and gradient descent, it just explains very well how gradient descent works. And you need that later for the neural network lecture as well. When you work in the lab session with machine learning libraries, scikit-learn probably, they are very simple to use. You just need to tell them basically your model. So you have you say, okay, I want to do regression or linear regression. Please fit a model based on the training and based on the data set and the labels Y. And then it kind of outputs the model that you then can use to make predictions. So it's really common to distinguish. It's all in one data set. It's all in one file typically, but you always distinguish between X and Y. Yeah, that concludes quite early. We have still time if you have questions, if you want to repeat something. Any questions? Do you understand how great this is? No, we are through now with the content for today. It was a bit faster than I anticipated. But if you have questions, otherwise, I see you next week again. Good. Thank you.